Okay, we ever take the integral from 0 to pi over 2, sine to the 7th x dx. Okay, I chose this problem specifically to actually compare methods on it. I didn't want the exponent to be too large. If we did 2025, it becomes all about the computation. And if the exponent gets lower, if it's like sine to the 4th, then you might be tempted to just use normal methods. But with sine to the 7th x, if you just kind of do normal trig methods, it's kind of tedious that way. So before we get started, let's take a look at the different methods I have in mind for this. Okay, so thinking about all the different methods, this is what I came up with. I may have missed something, let me know in the comments. There could be, I'm sure there's other things, but I came up with these 5. The first one we kind of discussed briefly there. I think just doing normal trig stuff, it's possible, but it's boring, it's tedious, and it gets worse if it was like sine to the 11th. I don't think you want to do that. So I'm saying it's possible, but I don't want to deal with that. Then coming down to number 5, you could definitely do it this way. There's probably multiple ways. I didn't look too much into it. I'm not going to do that here. But let me know if you think this way is comparable. It seemed like it might be kind of tedious the way I was doing it, but maybe you've got a better way to do this. So let me know if you did some complex stuff to it. And so with what we have left here, I think all 3 of these are really good methods. The thing about 2 and 3 is, to me, these are really the same thing. It's just a slight, maybe different way of looking at it. We'll talk about that, but I think these are really the same thing to me, but maybe you've got a different way of looking at that. And this is going to be a good way. I think let's do beta function first, and then we'll come back to this 2 and 3 case afterward. Okay, so we have our formula for the beta function over here. As you may know, there's many different forms of the beta function. This is probably a pretty common one. So what this will allow us to do is put this into the form of the gamma function where we can calculate it pretty quick. It is a little, I don't know, it's a little tedious with it is a little awkward using the formula, so it's not like a 2-second method, but it's still gonna go pretty fast. One thing I wanna do on it, so okay, we have our integral. We don't have this 2 out front, first of all. So I think let's do this. Let's rewrite this integral to get it set up in this form. So we just have a 1 in front. So in order to create that, I'm gonna write it like 1/2 times 2 to set it up for the formula. We have the integral from 0 to pi over 2. Then for sine, in order to get it to look like this, let's write 7 as 2 times 4 minus 1, just to use this. Where that way the a value on it is going to be 4. And then for the cosine value, we don't have cosine, but we're just creating it. So we want the exponent to be 0. In order to do that, I can write it like 2 times 1/2 minus 1. All that stuff is just 0. But then we've created a b value of just 1/2. So then going to the formula, we have our 1/2 value in front. All this stuff, we can put it into this. So we've got our a is going to be 4, b is going to be 1/2, plug in, plug in. So we got gamma of 4 times gamma 1/2 over, add those together, let's write this as gamma of 9/2. Now to reduce this, we've got the formula gamma of, let's say gamma of n plus 1 is n times gamma of n. So for gamma of 9/2, we can just reduce it like 7/2 times gamma 7/2. But if you just do this over and over and over again, what you're going to get is 7/2 times 5/2 times 3/2 times 1/2, and eventually gamma 1/2. So we'll take this and we'll plug it back in here. So for gamma of 4, we also have the formula gamma n plus 1 is going to be the same thing as n factorial. So gamma of 4, I can write that as 3 factorial over, we'll use the 2 here. We'll just leave gamma 1/2 for the moment. Then we need to plug all this stuff in right here. But then gamma 1/2 and gamma 1/2 can cancel here. This thing, 3, this is a 6, so I can actually cancel this with a 2 and a 3 here. And then I think we can put it all together. Flipping this into the numerator, 2 times 2 times 2 times 2, 16 over 7 times 5 is 35, and that's it. So that's method 4, I guess. And I mean, it is a little clumsy. I would do it faster in real life if it wasn't a video, but it's still, I think, probably kind of slower than the other methods, I think, but not too bad. Okay, next we have on the board our formula for the power reduction. This is going to work the same way for sine or cosine, doesn't matter. Our a and b value needs to be an integer multiple of pi over 2, or 0, of course. They both have the same structure. It's going to be n minus 1 double factorial over n double factorial. But this part is going to depend on if it's an odd or an even n value. But the nice thing about it is these two values are really easy to calculate. Like when n is 0 for I sub 0, then we just have like sine to the 0, but that's just going to be integrating 1, so that's going to be pi over 2. And I should say that's only pi over 2 in our case here, but this would work the same way for cosine. And then for our I sub 1 value, now we're just integrating, our n's 1, so we're just integrating sine. So in our case where we're going from 0 to pi over 2 minus cosine x from 0 to pi over 2, and this value is just 1. So getting to our example here, what we have is we're just doing the I sub 7 case. So what you can do is go to the formula n minus 1 double factorial. So that's going to be 6 double factorial over 7 double factorial. And we've got the odd case, so we're just multiplying by 1. Don't worry about that. For double factorial, let's just expand it out to reduce it. It's just going to be like factorial, but you're kind of skipping over one value for each of them. So this is going to be 7 times 5 times 3 here. I can cancel 3 with 6 and get a 2. And so for the solution of this, we get 16 over 35. Now, I think the reason I thought to do this is because my question was, why do people use Wallis integral when it's the same thing as this? But I guess the other way you could look at it is, why do people use this? So there's maybe some trade-offs. So like with Wallis's integral, one thing is you never really calculate this I0 and I1 value. You just kind of remember that when the bound, because in Wallis's integral, it's only going to work when you're going from 0 to pi over 2. And then doing it that way, you don't really even have to substitute in for this. Like you kind of just start with the point that this is going to be a 1 and this is always pi over 2. And you don't have to worry about any other case. So all you have to worry about with Wallis's integral is odd and even. That's it. The sine, cosine doesn't matter. You're not worried about the bounds. Usually my thinking on it is I would rather do the power reduction because it's more flexible. With Wallis's integral, there's nothing for if this upper bound's pi or if it's 2 pi. I guess the argument would be those cases are usually pretty easy to simplify. A lot of times when you have your integral, your similar integral, but you have something like you're going from 0 to n pi, a lot of times these, let's just say it's sine, I shouldn't have used n, let's say it's like sine k to the x or cosine k to the x. Well, a lot of these integrals simplify really easily. What I probably should do is do the cosine case, because when you look at this I1 value for cosine, well, this integral here is always 0 because you end up getting sine evaluated from 0 to some integer multiple of pi, so those are always 0. The other thing about it is a lot of times these easily reduce. You can usually, like Queen's principle, reduce the bound and get it into this form. Now, maybe this is all just nitpicking, but I do think it was interesting that sometimes people prefer the Wallis integral or the power reduction. One thing I should have mentioned on this is a lot like the power reduction for the indefinite integral, but what happens when you have the bound set up, all the complication, there's other terms that go away and go to 0, and so that's how you get this simplified formula over here. I have derived this in other videos, and I also have it on the website, so I'll see if I can find a link if you need some more information on the formula. Okay, that's it for today. Thanks everyone for watching. Have a good day.